Everyone, welcome to today's class. So let me just show you the quick syllabus. Basically, we had left a random forest slide somewhere halfway through. So we're going to finish the rest of the random forest slides and then move on to a newer topic as well. And that would basically be hypothesis testing. So we're doing this. We've covered the slides 6 and 7 before already. So we'll finish random forest and then we're going to start hypothesis testing. This is not necessarily machine learning. This is more of statistical foundations. It's very popular. Depending on what industry you're going into, it may be more or less popular. But it's a very standard topic in statistics, kind of foundational area. Okay, so I have my slides ready, so let's jump into the random forest slides. Okay, for some reason it's taking a while. So we covered part of it. We discussed some areas. This is a quick recap. We discussed what is known as bootstrapping, and which is basically using resampled data points, data records, resampled records, and also the fact that we are going to generate multiple trees and not one tree. So we generate multiple resamples, bootstrap samples, which are like subsamples of your original data set, and then we fit multiple trees. We grow multiple trees from that data set, and then we average the result of all the trees, if for regression or take a majority vote for classification. And then we were discussing about, okay, we need to grow multiple trees from the data set. Now let's figure out how we grow at least one tree so that we can repeat the process multiple times. Typically in production environments, people grow anywhere from 100 to 2,000 or 3,000 trees per one data set. So the tree you're seeing, you grow like hundreds of trees like that, and then you combine the results to get your final classification or regression, right? So we thought about what it means to grow a tree, and in the context of machine learning, basically at each node, so including the root, you pick one particular variable in your data set. If you had 100 columns, you pick one column that makes the most sense to use at that particular node, and then you try to come up with a decision based on only that column. Things like if some number is greater than this value in that column, then you go right. If it is lesser, go left, or or somewhere in some interval, you go through this or this or this, right? You make that decision based on one column at a time, one variable at a time, and then once that happens, you go to the next node. Now you take that column out from your data set, and now you use rest of the columns to make another decision. Right, you keep doing that, and once you reach the leaf node, you only have the decision, the final decision. So if you're doing, say, spam classification of emails, then all this gets done, and once you come to the leaf node, all you have is whether the email is spam or no spam, right? So now the question is, okay, now we understood what it means to grow a tree, but now still the question remains, when you say pick one particular variable out at each node, how do you know which is the best variable to be picked at any given node? Second question, given that you picked a variable, how do you know what is the decision you take to go to the next level, right? What do you do with that particular variable? Like, how do you make the splits in terms of your numbers and intervals? Okay, so then the question is, what is the criteria for these two things? The criteria that is used is known as information gain. Information gain is this function. It is basically a function of what is known as entropy. So I is denoting the information gain, H is denoting the entropy. Now the question was, what is the entropy, what is the significance of information gain, etc. This is just a bunch of equations you're seeing that are valuable, but you want to understand what is going on, right? So that's what we wanted to do, and we didn't really quite cover that particular topic, which is what we're going to cover now. Okay, so let me make a few things clear in terms of the notation. Okay, so it's backing up to this slide. Theta refers to theta j refers to any particular variable. So if you had many variables, one particular variable. Okay, I refers to information. I told you that information gain. You want to maximize that. Sj denotes subsets of your data, basically. So it's basically your data sets. So going forward, H is the entropy, and then the modulus kind of a thing that you see here is not the absolute. It's basically the cardinality. It's not absolute value. Cardinality means how many variables are there in the set inside. So how many so cardinality of S in the denominator means how many variables are there in your entire data set. Si means some subset of your data. If you take what is the number of variables you're taking in that subset of your complete variable set. Okay. And then now let's get into the entropy first. If you understand entropy, you will understand information gain a lot easily. So entropy is kind of analogous to probability, but kind of in an opposite sense, because in probability you're measuring high probability means highly certain, low probability means less certain. Entropy is kind of reverse. Entropy is measuring the uncertainty in your data or in your system that you're trying to model. So high entropy means more uncertainty. So it's like less probability, more uncertainty. And low entropy means high entropy means high uncertainty. Low entropy means there is less uncertainty in the system. So less randomness going on. Okay, and this is not negative, it's supposed to be equals to, so entropy is defined as the probability multiplied by the log of the probability of all the possible events that can happen. This is supposed to be S, not C. So given any subset of events that is possible, you are summing the probability of every particular event in S multiplied by the log of the probability of that event, and then you sum this up. This gives you the value of uncertainty in your system. The log is base 2 because you're looking at how many bits are really required to encode the information, right? So if more is required, then it's basically more uncertainty. So yeah, so this is the negative of, so equals to the negative of this. It comes from an area called coding theory or information theory, etc. Used now in machine learning, statistical physics, etc. Basically, if you had, say, so we are studying entropy a little more now. If you say had a discrete event X, so since I said discrete, so there's a fixed number of finite possible states. Say it had 8 possible states. Now the question is, how many bits are required to transmit the state of X, right? So X. So this could be, for example, the state of some player in a video game, right? You can say, is the character jumping? He's in a jumping state. Is he running? Is he firing? Is he dying? Etc. Right? Is he crouching? Is he crawling? Right? These are 8 possible states of X. But there, it is you who is playing it. There's not much of an uncertainty because it's a deterministic system, but sometimes it could be an uncertain system, like say tossing a coin, a simple example, right? So there is a lot of uncertainty in the result of what happens when you toss a coin, like a few times, and there is only 2 possible states in that case, right? It could be heads or it could be tails, etc. Now, from a coding theory standpoint, we are not going to go deep into it, but it's good to just state this, right? Which is, you want to know how many bits are possible to transmit this, are required to transmit the state of X, basically, when there is uncertainty. Right. So say, for example, in an extreme case, the coin was that you're tossing is highly biased towards only giving you a head, right? Say it is always giving you a head, extreme case, which means although it can take 2 possible states, you don't have to transmit head and tail, right? It's two different states that you're transmitting. You don't have to transmit that both, because to explain the state of X, since it is highly unfair and it always gives you heads, all you need to transmit is only one bit. That is the reason we want to take, when you are transmitting or coding your information or your signal to be transmitted from one end to the other, you want to take care the probability of these events occurring into consideration so that you can compress your signal further. But that is an extreme example because we don't have coins that always give you head. Now, say if all states are equally likely, and in this, now he's giving you this example, say some event that can take 8 states, right? So if you use this formula, all you do is you put in it into the probability times log of probability, and then you get the following. You get 3 bits basically. This is base 2. Okay, so basically, although you have 8 states, if I give you the information from probability standpoint that all 8 states are equally likely, all you would need is 3 bits basically. Let's calculate it a little carefully. So let's do it again. So say it can take the states A to, we call the states by letters, for example, A to H. These are 8. In that case, say if the probabilities are not equally likely, if I say the probability of A occurring is half, B occurring is 1/4, C is occurring 1/8. So as you go from A to H, the probability of seeing that particular state is becoming less and less probable, right? It's a very low probability. 1/4 is a very small number. Half is much, or 1/4 is much larger, right? So half probability. So if you just apply that formula, probability times log of probability, and you sum up everything. So half times log of half base 2, 1/4 times log of 1/4. Sum everything up, there's negative before, then you get a result 2 bits. So basically, to transmit this, all you would need is 2 bits. Okay. Anyway. So that is the topic of entropy. So what does high entropy imply? It means high uncertainty, right? So it exists from a uniform distribution. So there's like, everything is possible. It's like highly random. You can't predict really which one is going to occur more likely or less likely. A histogram, yeah. So a histogram of the distribution will be flat, right? So why would it be flat? Because every event will have equal probability or equal frequency of occurring. So it would be flat when you generate that experiment. What does low entropy imply? It means X is very varied from peaks and valleys in distribution, which means some values or events are highly likely. So that's why you have high probability. Some are highly unlikely. So you have valleys. So the histogram would be very many lows and highs, which means there is low entropy, right? Lesser uncertainty from completely random, being completely random. Okay. Similarly, there is again, just like conditional probability, there is what is known as conditional entropy. So you want to measure the entropy of some state given that some other variable is taking some particular value or state, right? So for example, suppose you want to predict output Y given input X. What is output? Y is miles per gallon. So this is something to do with vehicles, right? Automobiles. Y is miles per gallon, and say X is the number of cylinders in your vehicle or automobile, right? Okay, so, and then say you collect some data set, right? Maybe different cars, right? Ford, Toyota, whatever, Volkswagen. And then say you collected this table of data, right? So, and then you also classified your miles per gallon into, is it good miles per gallon or mileage or bad mileage, right? You took, say, 2 buckets. Say that was your data set. So these are the number of cylinders. This is whether it is high mileage or low mileage. That vehicle is. It could be one vehicle, multiple vehicles. I don't know. That information is not there. All you have is this data. Okay. And the cartoon example. So now let's see. 1, 2. How many goods and how many bads do we have? 1, 2, 3, 4 goods, and 1, 2, 3, 4 bads. So in your particular data set in this table, good and bad are both exactly likely. So it is a uniform distribution, right? 4 counts of good, 4 counts of bad. Probability is also half and half. Sorry, it's not half and half. Probability is always 1/8, right? Everything has 1/8. Anyway, so 1, 2, 3, 4, 4/8. Yeah, okay, it is half and half. Anyway, so, but the point is both are equally likely. Everything has half and half probability. So your entropy is the highest, since you have there is highest uncertainty, right? You cannot, everything is randomly occurring. You cannot really say in this record. So in this particular data set, h of y is equal to 1. But now if you factor into the concept, you're going to the conditional entropy, which is, say, what is the entropy of y given that x is any given number of cylinders. So now he's asking, if the vehicle is having 8 cylinders, what is the entropy in y? Is it still equally likely that you cannot predict whether it is good or bad mileage? Or if I tell you the information that it is 8 cylinders, if I give you that condition beforehand, is it more likely that it is skewing towards one particular decision with a higher certainty? So is it more likely good or more likely bad? Or is it still equally likely to be making it very hard to predict? That is what entropy is measuring. So the entropy of y among only those records in which x has particular value, say some value y. So here these are examples. If I'm asking entropy of y given that x equal to 5 cylinders, let's see, 5 cylinders, 1. So he said exactly equal to 5. He didn't even say like some interval, x between 3 and 7. He didn't say greater than or less than. He said exactly equal to 5. So in your records you have 1, let's do this carefully, 2 records have 5 cylinders, and both records have good, one record has good, one record has bad, which means it is still very hard to predict whether, if I tell you if it has 5 cylinders, it will always be good or always be bad. It is still equally likely happen. So then the entropy is the highest, so that's why it is 1. Now let's see, h of y given x equal to 8, where is 8? So 8, there is only one record and it is bad. So if anyone tells you based on only this data set is asking, if the vehicle has 8 cylinders, what is the certainty of the output? We are 100% certain. So which means uncertainty is 0 uncertainty. We are 100. So we have 0 uncertainty in saying that it is always going to be bad mileage. So h of y given x 8 equal to 0. So these are the two extreme cases. Now for some numbers, you will have some number in the middle, right? Because it may be more close to 1 or close to 0, somewhere in the 0.5. So depending on what cylinders you're looking at. You can also look at intervals, right? What if it is between 4 and 6, etc. So that's the idea of conditional entropy, very similar to the idea of conditional probability. Okay, though similarly the formula is exactly the same. You are only multiplying the probability of event, but with the conditional entropy, basically, with the log of the conditional entropy. So now, by the way, now we want to cover the information gain. This is what is used in random forest, and it is a function of entropy, basically. So this is a very interesting topic. It's very intuitive to understand. So information gain is basically, say, information of gain y given x measures reduction in entropy of y as a result of knowing value of x. So basically, if I did not give you x any condition, then which means you're looking at the entire data set, right? Because you're looking at all the whatever 8 records you have here. So that is then the entropy you're looking at in the system. Now, if I give you some information about cylinder, then again you're looking at the entropy of the mileage, right? The conditional entropy. Now, if I give you any one particular value, right? If I say x equal to 5 or x equal to 2, then depending on that, your conditional entropy is changing from being high or lower conditional entropy, right? So basically, the information gain is given that some value I'm feeding into the another variable, how much more certainty or useful information am I gaining from where I was previously without knowing that information. Say if x was a completely useless variable, say if x was some variable that has nothing to do with mileage, say x was, say, the color of the hair of the driver, right? So assuming we are not racist or anything, we would assume that the color of the hair of the driver has nothing to do with the mileage, right? But then again, someone might say, maybe there is nothing to do with racial stuff. Maybe it is something to do with age. Maybe the color of the driver, if it is completely white or completely gray, maybe he could be a very old person or reasonably old person. Maybe he drives carefully, right? Then there is some certainty, but then it could be something else, which is a complete uncertainty. Say X is the number of trees in the backyard of the driver, okay? So, or in the garden of the driver. It makes no sense, right? It has nothing to do with the mileage of his car. Okay, so in that case, the uncertainty is high. So, and then even the information gain of me giving, even if I give you like million records or like a trillion records of every person in the world and what is the number of trees if he has a garden and how many trees does he have in his garden, If I give you like even like big data, if I give you a full cluster and data center of data, you would still not be able to predict whether his car has good mileage or bad mileage. Okay, so that's a funny example, but it makes sense in this explaining this. So the information gain you get in me giving you that X variable in reducing your uncertainty is completely zero. You're not gaining anything. You're where you are. Okay, but if I am giving you something useful in predicting Y, then your uncertainty begins to reduce because of this difference, because this is giving more information and this is whatever information you had before. So your certainty reduced a little more here than where your uncertainty was here. That is information gain. Now this is very useful, right? Intuitively, if you're trying to, coming to your tree example, trying to figure out what variable if I use, would I have more information gain? Is my uncertainty reducing in trying to predict the class of the email, whether it is spam or no spam, or whatever your problem was for classification in machine learning. And also for answering, once you have a variable to choose, what value you need to take. If I choose some variable, and then if I know what value I need to split that node at, then I can split that node exactly at that value. I can put that condition here and say go to here. If some other condition, go here. I can decide that condition based on any variable, as well as pick what variable at any given node using information gain. This is completely computable on a computer, right? And if it's a small tree, you can as well do it on a paper. So what is information gain used for? Some more examples. Suppose we are trying to predict whether someone is going to live past 80 years. Interesting, right? From historical data, we might find information of long. Now I'm giving new variables and seeing how much gain I'm getting. And what you're trying to predict is long life. Before we were thinking spam or no spam, now we're looking at whether long life or no long life, right? Assuming past 80 is considered long life. So the information gain of someone living long life, given that you give information about his hair color, is so and so. If I give smoker, it's somewhat higher. Information is gain is increasing. With this here, you're not gaining anything, right? Hair color has very little to do. It's not zero, but very little. Maybe whether how is balding pattern or I don't know gray pattern, I don't know, right? Based on that, maybe if someone is 95 years and he's perfectly colored hair and proper hair and no graying or balding, then maybe it's a good thing. Maybe it is, maybe it's not, but it's not heavily influential on long life. Maybe even if he's bald, it doesn't matter. Maybe he can still live 95 years, he or she, right? So it's not much gain if I give them. Smoker, it is giving a lot more information, because smoking, as we know, right, it can cause a lot of ailments, especially things like lung cancer, right? So we know a lot of things can affect your long life if you're a smoker. Gender, we've been studying before that, we had that a slightly higher proportion of women have been having a longer life than men in general. Similarly, day of birth has nothing to do, right? You could be born on December 31st or Jan 1st or something. It has nothing to do with you. So this has very, very, very low information. Even hair color has slightly some level of certainty it is bringing into your equation than day of birth. It has nothing to do with whether you'll live past 8 years or not. That makes sense. So these are the examples, right? So this could be your, say you had 4 variables, and this could have been your predictive modeling classification problem in machine learning. I give you million records of this data of how much life they had and hair color, right? And you can obviously draw a random forest. You will look at information gain 4 variables, then you say, hey, gender is having the highest information gain. So my root node will be gender. Now the question is, what split do I do for gender? Do I say if gender is male, go left, or gender is female, go right, or something else, right? So that is the thing. Then you go to smoker. This is the next most important variable left. So you first take a decision based on gender, and next node you take a decision based on smoker. Then you look in smoker, light smoker, chain smoker, or some combination, or maybe someone who smoked for 50 years and then stopped smoking, etc., etc. Or someone who smoked when he was a teenager and then he stopped smoking the rest of his life, all these things. Or he's been smoking since his teenager all through his life. Again, those are the different notes you can take. Then after that, your next decision would be made definitely not based on day of birth. It would be based on hair color. Then your final decision based on day of birth. Then your final leaf node will have, okay, this person, since he traversed like this in the tree, he's going to have long life. Other this person, he did very bad things with respect to these variables, so he's going to have less long life probability. So you make that classification in the end. Okay. Now this is another funny example, but a little more bigger data set. We are exactly halfway through our class. It's 9 o'clock, so we will be packing this up since we are done with this, and then we'll be moving to hypothesis testing. So let's focus on this example. This is the Simpsons, popular TV show, and there are different characters in Simpsons, right? Homer Simpson, Marge, Bart, a lot of other people. I don't even remember these names. But anyway, say I give you a data set of their hair length, their weight, and their age. And I want to classify, building a model and trying to classify, just giving this information, I want to figure out whether the person, the character in Simpsons is male or female. Okay. So say let's do one example. Say Homer Simpson, right? Hair length 0 inch, weight 250. It's kind of fatter, on the fatter side. Age 36. Right, Marge, hair 10 inch. You can see in the picture, he's got a very large hair, long hair, 150, 34. Okay, Bart, so-and-so, Lisa. By the way, Homer, this guy put in this Homer Simpson's photo here. It's supposed to be here, right? It's not in the header. So that's why you see Homer Simpson 0, like he's bald here. Okay, Marge is this lady, 10 inch. Okay, Bart is this guy, 2 inch. So Bart has lesser hair than his mother. Lisa has so-and-so 6 inch. Okay, anyway. So now based on this information and weight, right? So Bart and Lisa, much low weight. Maggie, someone is like only 20 pounds, right? Maybe some kid, age is 1 year, right? So and so. We want to figure out whether it's male or female, right? Now, in, say some test data set, some comic guy will come, and then he'll give you information, hair length 8 inch, weight 290, age 38. He won't give you his photo. Then you have to figure out male or female. If your model random forest is good, it will try to do these things with higher accuracy. So now so this is your tree, right? First you have all characters. These are the characters. The first guy is Homer, right? Now you want to figure out, do you split based on hair length or do you split based on something else, right? Based on weight or age. So anyway, so we compute the information gain for all the variables, and then say they got the answer that, say for hair length, you have the highest information gain. So first split is not made based on weight or age, but based on hair length, because hair length seems to be a better indicator of gender than age, right? Age, you can have old, young, middle age everywhere in both genders, more likely. So you split based on hair length. Now the question is, what is your split condition? Is it, if you do, is the right condition, say 5? If you say less than equal to 5, then male, and if you say greater than equal to 5, female, right? So if you see in less than equal to 5, you have a majority of male. You had 3 male, but 1 small baby. She's a girl, but she ended up in, baby girl ended up being in gender male bucket. Here also one mistake happened. This clown guy, he has some very weird hair pattern, and so the random forest got confused and thinking this clown hair is a female hair, right? This kind of mistake. But at least it's better than, it's not like still bad, like still reasonably okay. Now if you take some more conditions, say age and something else, maybe your accuracy will start improving, weight and everything. Okay, so that is exactly what is going on. So say this is entropy for some condition, right? You're measuring the same thing, probability of hair length being so-and-so, weight being so-and-so, age being so, probability hair length being greater than 5, less than 5. You can measure this, right? Probability times log of the probability. And you can measure information gain. Current set, complete minus what is the information gain when you take this hair length into consideration, right? So and so. Similarly for weight, similarly for age, right? Then you get information gain for all 3. Then you see of the 3 features, apparently weight actually was best. So in this particular data set, so interesting. So the hair length came later. So they started, since it is Simpson's characters, apparently the mathematics tells us that if weight is less than equal to 160, then it is female, greater than it is male. Again, obviously clown ended up here. So male, all are correct now, all 4. But now before he had 1 mistake here, 1 mistake. Now here 0 mistakes in male, but 1 mistake in female. So this is 1 false negative. So this is that guy here. Okay, then if you take hair length into consideration, now you have perfect result, right? Although he fell, so your classification is if weight less than 160, then go here, and then if weight less than 160 and hair less than 2, then it is male. If hair not less than equal to 2, then it is female. Now you have perfect classification. So this here information gain, you chose weight, and then you chose split based on 160, same thing. Then you thought next best information gain is hair length, and your split was based on that. This is a random forest. Okay, this is a good cartoon example. Okay. Okay. Any questions? All right. So we are 9:10. Now we'll get started on the hypothesis testing. I have that open somewhere. Let me open that again. Okay, so this. Okay. Okay, now let me give you a quick some sort of an intro on what topics we'd be covering in hypothesis testing and where these would usually show up in industry or whatever, your work, research, etc. So you're going to cover hypothesis, what it is, what it means, and then we're going to cover some specific hypothesis tests. One is very popular. I mean, all of these are very popular, especially the t-test is very popular, z-test is popular. Z-test is way too simple assumption, so not used as often as t-test. Chi-squared Fishers are very, very popular. You know, in a lot of companies and areas, say like advertising, there's some, or like even in pharmaceutical stuff, there is something known as an A by B test. That is what people use in industry. They call it A-B test or A by B test, or A-B test, right? A-B-B test, etc. So this test refers to what is known as the chi-squared or the Fisher's exact test. So they don't use this term in industry. It's like slang term. They call it A-B testing. Now, if you've not heard of A-B testing, for example, say New York Times website or CNN website, for example. Let's literally open CNN here. You can see my screen, right? Yeah. Let's open CNN. For some reason, CNN figured out the best spot should be given to this news article about some murderers in here, and the next news article is here, next is here. These three got highlight, projection at this particular time, 9:10 a.m., right? And then it figured out that the order of news item should be like this, and then when you scroll down, it figured out this bigger box has to go to this some celebrity stuff, so ad should go here. CNN internally is doing a lot of A/B testing. It is trying to figure out if it puts this here, it will have a higher viewership or higher reader engagement, higher click rate, or if it put it somewhere like one line here, it will have higher engagement. Apparently, based on its data, it figured out, okay, at this point of time, this being here is the best thing. So how do you test whether you choose a choice A or a choice B to go in each given place? This is known as A/B testing. And CNN does it on the fly in their production systems, and so does Amazon. So this is all A/B testing. Or when you're making a change to your way you're using ads, do you want to use ads with more feminine colors or with more masculine colors, right? Do you want to use ads with a lot of pink or no pink? Do you want to use a lot of ads with a lot of sporting material or with, I don't know, some clothing material? All these decisions are made based on A by B testing, and the companies make statistically significant experiments to make those decisions. It's not like some editor comes up every second and says, since it is running 24/7, you won't have some person like sitting on call and saying, hey, now this news happened, let's put it here. No, let's put it there. That's not how you serve CNN to like millions of customers, right? It is automated, and you take statistically significant experimental decisions. And that is known as A/B testing, and this what they use is chi-square and Fisher's exact test. Now, these are some concepts in terms of what are the errors and metrics involved when you do hypothesis testing. There is something called type 1 error, type error. There's a concept of p-value. So we're going to study these. Okay, so coming to the slides. Okay. So this is like contents table. So don't think too much about it. We will explain one at a time. Okay, it's just contents in here. So let's see what all he covered. So there is basically two kinds of when you take say hypothesis testing, you are testing for some hypothesis. Do I go with one option or another option? So basically one option, default option is null. If your data says no, if you go with alternate option, then it is alternate hypothesis. So you have two hypotheses. That is just the terminology. And there are two kinds of errors I mentioned. I will define these later. Right? These are some simpler tests to start studying. So one test could be about population mean when your variance is known. So if you're measuring some data set, right, some variable, and then you want to know want to test based on population mean. Someone says, hey, I think the average age of people, average life span of people who smoke heavily is 60 years. Another guy says, no, that is not what I think. I am hypothesizing that it won't be 60, it won't be 90, it is maybe 67 years. Now you want to figure out, right, which one to go with. Based on your data, what do you think is the better decision, more likely, and where you're making lesser of these errors, right? So that is a hypothesis test based on mean. But sigma is known, which means I will also tell you, hey, it looks like, although I'm asking you this question about the lifespan of smokers, I'm also going to give you some additional information apart from just the data about their lifespans. I'll also give you, say, what is the variability of the data. So you would know maybe the lifespan of smokers varying heavily, or it doesn't vary much. That is also known. Given that additional info, how do I choose whether it is 60 years or 67 years is more likely for their lifespan after which they die? Similarly, population mean when sigma is unknown, it's a slightly even harder problem. I won't even give you variability information. I'm directly asking about the lifespan given smoker, right? Population proportions. Proportions usually very popular again, say click-through rate, right? In the CNN example, click-through rate is what is click-through rate? Is basically the number of clicks you're getting divided by the total number of visitors, right? So say I visited CNN, I did not click any of those news articles. So I gave them 0 click-through rate on all those news articles. But I might have, if I was having a leisurely and not in this call, maybe some particular topics of CNN I'll be more interested, I will click them. So then they know these click-through rates. So they know click-through rates of all their audiences for each of every single article, every single advertisement. They know which is getting more popular, which is trending. So you are having different proportions. So you have 50 people out of a million viewers click this article. Some other article, maybe 500,000 people of 1,000,000 people clicked it. So these are proportions. Now you want to say hypothesis test about population proportion. Is this value or is it that value? Similarly, now there is a question of sample size, right? How do you decide what is the sample size that you would require if you're doing a hypothesis test about the mean, right? About, say, like I gave you the example, right? If you're a smoker, you're going with trying to hypothesize and figure out which one to go with, whether the person's lifespan will be 60 years or 63 or more than 60. You can have multiple also. You don't only have to have binary every time, right? So then the question is, can you answer with 99.999% certainty or high probability that you will go with one or the other only if I give you 2 samples? If I only give you 2 people, right? Some who are smokers and give you their lifespan, is it? Maybe you can, maybe you cannot. Maybe there's not enough information. What is the minimum sample size required? It's more likely that you would need more data, right? But would you need like 1 billion records? Maybe not. Maybe 1,000 records are enough. How do you figure out, given a fixed confidence or probability, how much sample size to go with? So now hypothesis testing, right? Like I said, can be used to determine, this is the structure of what are involved, right? Whether a statement about the value of a population parameter should or should not be rejected, right? So null is what you go with. If you reject it, you go with alternate. These are 2 possible hypotheses. So usually null is the default option. So less risk option sometimes. So say if you're doing a hypothesis test about, you take some DNA evidence of some crime scene, and based on that DNA evidence, you want to figure out whether the criminal is a murderer, a rapist, or a serial murderer, right? Or a burglar and that kind of thing, or if he's innocent. So ideally, you want to choose, if you cannot, so if you do not want to reject the null hypothesis, if you don't have enough evidence to reject the null hypothesis, then it would be more likely that you want to choose that the person is innocent, right? Only you want to make him guilty if you have enough evidence. Because you don't want to make the error of saying an innocent person is guilty. That is, you want to do that less often than saying a guilty person, making a mistake of saying a guilty person is innocent. So here the null hypothesis, you can say, I will say null hypothesis is the person is innocent given the DNA evidence. Alternate hypothesis, the person is definitely criminal given the DNA evidence, right? So now based on your DNA evidence data, you have to figure out, run some statistics and say whether you go with H0 or HA. H0 is null, HA is alternate. All right, developing null and alternative hypothesis. it is not always obvious how the null and alternate hypothesis should be formulated, right? So choosing what is null and what is alternate also, of course, something to be taken care of. Care must be taken to the structure of the hypothesis properly, right? The context of situation is very important. Yeah, this is some generic, statistical consulting kind of philosophical ideas which are used. So in some cases, it is easier to identify alternate first. In some cases, null is easier. So, anyway, this is generic statements. Now again, getting into more concrete stuff. Okay, these are some examples. So say a new teaching method is developed that is believed to be better than the current method, but you have to test it, right? You cannot say we will use it the new teaching method. So alternate is new teaching method is better, null is say new method is no better than the old. So if no better than the old, you go with null. If you think alternate is better, you reject null and go with alternate. Okay, similarly, new Salesforce bonus plan is developed. These are definitely business questions that even BIs get asked, right? Or even scientists, whatever. New Salesforce bonus plan is developed. So Salesforce is a popular company, right? Or maybe this could just be your sales team. That's what he means by Salesforce. Bonus plan is developed in an attempt to increase sales, right? Because you want to give bonuses to your sales team in a right way, and then you want to assume that it will increase your sales. Now, the hypothesis is the new bonus plan alternate could be new bonus plan does increase the sales. Alternate is new bonus plan has nothing to do with increased sales. So if your data says this, then why give the bonus, right? It's no point. Unless you want to not increase sales, but increase your retention or keep your sales team happy, then okay, maybe this is good. This is alternative. But for the sake of increasing sales, maybe it has nothing to do with it. And based on that, you can take your decision. New drug is developed, right? Pharmaceutical, with the goal of lowering blood pressure more than the existing drug. Now you obviously have to test it. Apart from testing other things, whether the drug is safe and everything, you also want to test the efficacy of the drug, right? You don't want to send a medicine that is just like a sugar pill and does nothing, and people are buying thousands of dollars, right? So FDA wants to know that the drug really works. So how does FDA clear a medicine for your aisle or your pharmacy? So basically, he does a lot of statistical testing. So there, the hypothesis: new drug lowers blood pressure more than the existing drug. It doesn't have more effect than the existing drug. Okay. Now we've done enough examples. So one final example: right? Label on soft drink bottle states that it contains 67.6 fluid ounces. Is the label correct or not? Right. Greater than or less than. Here it is known as this is known as a one-sided hypothesis because you're looking at a greater than or less than. If you look at interval, if you say it is between this value and that value, then it's called two-sided hypothesis. Now, yeah, this is what I was talking about. This one-tailed hypothesis. You are using greater than less than simples in your null and alternate. If you are using that, here it is lower tail. If you are using in this order, especially for your alternate, you're using less than. For your alternate, you're using greater than is known as one tail. It's a one tail, but it's upper tail. And if you're using interval or if you're using not equal to or equal to, then it is known as two-tailed hypothesis. You can also use interval here, but yeah. Okay, so now, and by the way, why is this two-tailed? Because the value you're saying it is not equal to, it means it could be greater, it could also be less than. You don't know if it is this or this, the alternate. That's why it's called two-tailed. That's what I mean by interval. Okay. Okay, some nice story here. Now, major West Coast city provides one of the most comprehensive emergency medical services. So something like 911 services, right? Emergency medical, paramedical services in the world. Okay, some city. Operating in a multiple hospital system with approximately 20 mobile medical units, so 20 ambulances and everything. The service goal is to respond to medical emergencies with an average response time of 12 minutes or less, right? Someone is having a cardiac arrest, heart attack, whatever, right? Asthma attack, right? You want ideally the emergency service to arrive as soon as possible. You don't want him to arrive after 12 days or 12 hours, right? The guy might as well die by then. So you want to reduce this, but they are making a claim. They're saying we are the best and we have these many units and we are making sure our average response time is 12 minutes or less. Now, obviously, some cases it may take 30 minutes, some cases maybe 2 minutes, right? But you want to look at average time if it is less than 12, right? So lesser the average time, less likely that you will see more 30 minutes often. You will see this more often. So the director of the medical services wants to formulate a hypothesis test that could use a sample of emergency response times, right, to determine whether or not the service goal of 12 minutes or less is being achieved. So this is a typical hypothesis testing question, right? So this is what is this? This is a one-tailed hypothesis, but upper tail because your alternate is greater than symbol. So this you want to test less than equal to 12 is null. So if you have enough evidence to reject that, it means it is greater than, then you reject it to the alternate. Right? Now, what are the kinds of errors that you can make? Type 1 error, type 2 error. Very important, right? Type 1 error is rejecting H0 when it is true. So that's a false decision you're taking. If your hypothesis test calculations are not good enough and your way of doing test is wrong, right, then you'll be making type 1 errors as one possibility. The probability of making a type 1 error when the null hypothesis is true as an equality is called the level of significance, right? It's also taken considered by a letter called by a symbol called alpha, which means if your alpha is 0.01, which means your chance of making a type 1 error is very low. It's 0.01. But maybe not be good enough, maybe 1.001, but sometimes it's good enough. If it is 0.9, it means very likely 90% of the times you're committing type 1 error. So better not go with that methodology or your testing or your computations, your mathematics. Applications of hypothesis testing that only control type 1 error are called significance tests, right? There's another kind of error. It's the other way around. It is before I said it is rejecting H0 when it is true, right? That is type 1 error. Now it is accepting H0 when it is false is another kind of addition you can take. That is known as the type 2 error. Right? It is now there is a theorem. He just wrote it is difficult, but in the books we've read, right? If you see more rigorous textbooks, you will see that there's a theorem that it is difficult to control for reducing both the type 2 as well as the type 1 error, right? Especially the type 2 is difficult to control, but also the combination of it because you cannot reduce both. But you can keep both in some reasonable balance and check which is good enough for you to go ahead with your decision. Statisticians avoid the risk of making a type 2 error by using do not reject H0 and not accept it. Anyway, this is confusing for you. Okay, type 1 and type 2 errors, right? This is in your case of that example, whether the emergency response service response time is less than equal to 12 null versus it's greater than 12, he wants to decide by looking at response times of different cases that they've handled, emergency cases. So this is the correct decision, right? When it is true and if you conclusion is also accept true, H0, well, true. Well, if the truth was null and you also accepted null, then it's correct decision if you did. But if you accepted null when the truth is false, it's type 2 error. If you accepted when it is, if you rejected when it is true, it is type 1 error. Again, if you rejected H0 when H0 is false, then it is correct decision. The greens are this is just like your confusion matrix. Your diagonals are correct decisions in the hypothesis test. Off diagonals are wrong decisions. Okay, now what is p-value? We mentioned this. This is the last term we mentioned in our contents, right? We talked about null, alternate, type 1, type 2, then we also talked about p-value. So the p-value is also very important, very popular. It is basically, he wrote in so much story here, but it is basically the probability of, falsely rejecting the null when it actually is true. So let's see if that is what he wrote. Okay, he wrote about how to compute the p-value. And he made a decision based on the p-value. So basically when you run a hypothesis test, you get a p-value, and then alpha is the significance of type 1 error you'd be okay with. Say if your alpha, you want to be very nice, very good results, and you would put your alpha very low, right? Because your chance of type 1 error, you want to be very low, say 0.01. You don't want to take any more chance than that. So now say if you got a p-value that is greater than that number, then you would say, oh, then I would reject. I do not have enough evidence to reject. If it is less than that number, you have enough evidence to reject. So basically, your p-value is basically, I have to draw a distribution and show it is basically the, yeah, this one. So when you look at the structure of a hypothesis test, so the p-value will take a while to explain, so bear with me. When you take the structure of hypothesis test, what happens is the follows. Say you're doing a hypothesis, in this particular example, population mean, but the structure is same for more complicated hypothesis tests as well. The structure is you basically compute what is known as a test statistic. Okay, it is very common terminology, test statistic. Basically, test statistic is some computations you may do on your data set, and based on the result of that test statistic, you will decide whether you go with null hypothesis or with alternate hypothesis. So now say this is a popular test statistic for this population mean test. It is this is known as the test for mean. The test statistic is this value, x bar minus mu naught by sigma by root n, right? So basically mu naught is the null number that you're putting in your null hypothesis. So say mu naught could be 12, for example. You want to see if how far the average is really from 12, and you want to take the noise and variance into consideration in the denominator. So this is like signal to noise ratio. If this is signal is high, means more and more difference you're seeing in your data set from what you put in 12, it means much higher than 12. It could be on the greater side or lesser side. Similarly, here less variance means less noise, which means your test statistic is more confidently making decision. But if your signal is very less, if you're looking at your data set is 12.1 and you're testing against a null of 12, it's very hard to make decision, only 0.1 difference, right? Whether you go one side or the other side. And if your variance is very high, it makes it even harder. So you want to have low denominator, high numerator. It makes it easier for the job. Now the thing is, since you're looking at random data, random uncertain, you're looking at statistics, there is some uncertainty in your data always. So even your test statistics, since it's a computation of your data with some uncertainty, even that will have some distribution. This is known as the sampling distribution. Say your test statistic also, some values it can observe with high probability, some values it will see with low probability, right? So when the null is true, this is what you're assuming. If the null is true, you're assuming that your test statistic is this and it will have this distribution. That you're computing this through theorems, because you can compute through theorems. If I say your original data is some distribution, this value will always be normal distribution based on what is known as the central limit theorem. We've not discussed the central limit theorem because it's more mathematical side of things, but we will discuss it in the future. But I know that this distribution, this quantity will always be normal, regardless of whether your data set is normal or not. It will always be Gaussian data. So there, since this is low, so if your null is true, you know that if the true result is that null hypothesis is what you need to go with. So if your null hypothesis is true, then you will know that since this is a distribution of the test statistic, you will know if you compute this on your data set, you will know if it results in some value of this amount on the x-axis, or some value less than this amount, like these values on the x-axis, then you know that it is highly unlikely to observe such a test statistic when the null is true, because the probability is low. But if you see a test statistic around this value, then you know it is highly likely to see such of a test statistic number when the null is true, which means here you have more confidence in saying the null is true. Here you have very less confidence in saying null is true, so you have to reject the null. So the p-value is the cutoff point, right? Is this the cutoff point? Greater than this, if I see it is highly unlikely to observe, so I will say I will reject null. Or is this the cutoff point, or is this the cutoff point? Because you see the probability is getting low. So that choice of p-value, that is known as the p-value. What is the value, so that beyond that you can reject the null hypothesis. So this is known as the p-value. I am sure I have thrown a lot of things in this last slide at you. There are things I know and you are learning in the beginning, right? So it might seem that way, but after looking at this a few times in the coming classes, things will turn around. You'll have reasonably enough understanding from where you are right now on this particular topic. So we will definitely dig into this a little more slowly and a little more carefully as we continue it in the next class. Any questions by the way?
Pranit, so you gave the example of hypothetical testing, the CNN example, right?
Hypothesis, yeah.
Yeah, so on what basis do they decide which one to show on the left and right? Does it based on the priority of the news, or do they have the keywords like Trump or North Korea or something like that?
So they have a lot of variables. CNN is a big company, right? It's a big headquarters in Atlanta and a lot of companies everywhere. So the variables you mentioned, obviously they would also use more than that. They would use a lot of information. But you're asking a question of not about how they're doing hypothesis testing, but more about what data you're feeding into your hypothesis test in CNN to make that left or right edge. So obviously, none of us work in CNN, but we can guess that we use some more variables than just the two variables you mentioned, although those two are important. So it depends on the situation, right? When you train when you design your experiment, let's think about it. there is some reason your background is always white. Your background is not like rainbow colors, because CNN knows that having rainbow colors as your background is not going to. It's obvious, but they also take that decision statistically as well. But then someone might say, hey, maybe gray will give us better. Then you have to test whether I use gray background or not. What will you do? You want to see if your readership is increasing or reducing. You want to see if within your readership, your click-through rate is increasing or decreasing. Similarly, it is more easier to instead of the color, you'll have more signal if you're talking about this thing should be here or here, right? Or maybe somewhere low or above. So you're running a hypothesis test every time, and you're typically looking at what is known as click-through rate. You want to definitely look at how many clicks you're getting if I put this here versus if I put it here. Similarly, if this goes here versus here, then maybe CNN figured out that in this combination of left and right, this being on the left and this being on the right, you are getting the best of both worlds. And because here, although your reduction in click-through rate is somewhat there, but here the gain in click-through rate is much higher. So you're looking at the difference in click-through rates, difference in proportions, right? How do you compare proportions? That is what is known as a chi-square test. Proportions. There you go, chi-square test for proportions, or you can also call for binomial proportions. We will study this test, but right now in our slide we only studied what is the structure of hypothesis test in general, but we will get into specific hypothesis tests. So basically you will have a 2x2 table, right? Say this is the CNN example, or say some healthcare example. CNN fits here as well. Say I'm giving you some medication. The question is, one count of medication is good or two count is good to control the disease, right? This what it is. So now you know, if you give one count, this was the result for this disease, this was the result for this disease. Then you want to see which one you go with. So you put this versus this, and this to the left and this to the right. So similarly, this could have been ads and this could have been left and right placement. Then you can figure out the right answer based on some computation that is known as chi-square hypothesis test. You would get some results, p-value, everything. Then you get the final answer. That is the overall structure that you're doing. We will get into that test in detail, but yeah,
okay.
It's a creative thing, right? You gave up some examples. So click-through rate is one thing. There could be other variables that they look at as well.
Yeah, they are also changing the size of the image or the news based on.
Yes, there is so many things. All of these are considered. Yes. There is also something known as a cost per action or cost per click, CPC. Say we thought of click-through rate. Now let's see cost per click, which means this is more useful, especially for advertising, right? Because here, for example, okay, Hulu. This is an client, right? Advertising client for CNN right now. So Hulu. Yeah. Now I have not clicked it. So a lot of people might have clicked it. The more you click, the more gain for Hulu. So click. Then CNN can say, hey, we are a world internationally renowned news channel. If you advertise on us in this spot, we will guarantee that within 1 week we will reach 70,000 customers or 7 million customers that will click your ad or whatever that number is, right? That is the CTR, the click-through rate for this Hulu ad. Based on that, they can charge Hulu because they have two numbers to say. One thing, they can say our readership is 10 million. We will ensure that 1 million will click your ad if you advertise for 1 week. Since 1 million is a big number, we are reaching out a lot of people, you have to pay us $5 million per day to advertise in here. So you have to pay us $35 million to advertise for 1 week on CNN in this part. So Hulu will say, okay, we want that advertising, so we will pay you. But if CNN had other numbers, say bad numbers, if it had 1 million readers or 10 million readers, but only 10 people are going to click, it doesn't have enough evidence to ask Hulu $5 million every day. It will ask $5 a day to advertise to reach 5 or 10 people. Right? So this is the click-through rate of Hulu. At the same thing, the cost per click, which is the amount that Hulu is supposed to pay to get every click on its, for every click that it gets, what is the amount Hulu pays is also decided by how well your CTR is, right? So based on that, the cost per click for Hulu increases because CNN is popular. If it was on my homepage, Hulu will have to pay maybe 0.001 cent, but here it might have to pay $1 million every hour. You never know.
But how does CNN know that how many clicks Hulu is going to get before they display the ad here?
So this is a purely software engineering concern. This is not a data science concern, right?
Yeah, I mean, exactly.
So it's all to do with the cookies and tracking, and these days you will be, even in AWS, I cannot share what variables I'm going to be looking at as internal, but I can guarantee that you will be surprised by how much information we know about you just based on what you're doing, not only on Amazon, what you've done in your clickstream before reaching Amazon and before, after finishing your work in Amazon, we still know where you're ending up and where you came into Amazon from. So if you are more likely some hacker guy, you would be searching for API keys on that you can steal on GitHub, and you'd be searching a lot of black market, for stolen cards and all that, and then you would end up into Amazon so that you can use that information in a wrong way. But if you're like a true shopper or someone else, you would have a different pattern. From a fraudster, there's no fraudster, and we collect more than about 700 variables about every single person, just based on what they're doing in Amazon. And obviously it will also involve things like what has your click-through rate been internally, what is your other thing, what is your, how your mouse is moving, how quickly you're moving, how you're typing, are you doing repetitive stuff, from where you came, what your IP address is, what region your internet provider is. Is it Comcast? Is it XBT? We know that internally. There's a lot of things, what is your email login? Is your email looking like raghu.kulkarni at gmail, or it is looking like rxyzafml at hulumail.com, which means you probably automatically generated a bunch of emails that you don't care about just to do fraudulent things, right? Different things. So even a good user, we have like about 700 variables that we're collecting. So there's a lot of information we know before making that decision. Same thing, CNN, I would give the benefit of doubt to CNN. They're not just collecting click-through rate and cost per click, they're collecting maybe 500 or at least 100 variables about every click on an ad.
Hey, Tanis, I want to ask you one thing about the A/B test.
Yeah, sure.
Yeah, for the A/B test, there are only two hypotheses, right?
Yes.
It's above or beyond, like a picture. I put it on the left or put it on the right.
Yes.
But if in the web page there are thousands of places we can place the picture or place a line of words, right?
Yes.
Which will means we're gonna do thousands of A/B tests just for this one single position of the picture, right?
That's right.
Okay. Wow, that's tons of work. So
that is a lot of work. This is automated internally, and by the way, there is another thing that comes into play. If you run one A/B test, it is more easier to make a decision. If you run like 20 pairs of A/B tests or 100 pairs of A/B tests, right, for different sizes of SMB, you need to aggregate these decisions together to make your final decision.
Okay.
The cost of aggregation makes it a lot more harder because it brings up a problem that is known as a multiple hypothesis testing problem. It's not binary hypothesis. It's not hypothesis. Multiple hypothesis testing. There is a problem that would be your results would not be as significant and as easy decision to make as it would be if it was a single hypothesis test. And this is known as the false discovery rate problem. I'm sharing my screen. If you see, if I just did hypothesis testing false discovery rate. So what is, I mean, I've not discussed with you the mathematical aspects of a normal single hypothesis test. So we will get into this problem, the multiple aggregation problem in the future, but I want to mention that it makes job a lot more harder, even from the statistics side of things. Because what would have been significant for one single test is not, that level of significance is not enough if you're having multiple tests. You have to be, like, say, if 95% confidence was enough in making a decision for one test, only one A/B test. Same 95% confidence, if you put as your standard for 100 hypothesis tests to aggregate, it is not good enough. What the theory says is, if you're running multiple and aggregating, your confidence level for each test should be 99%, for example. You have to take a decision with 99% accuracy for individual tests, then only you can aggregate, so that your aggregated decision will at least have 95%. That kind of thing. So yeah, but that is true. That is what happens in reality. It's known as the multiple hypothesis testing problem.
Okay, understood. Thank you.
Yeah. Okay, so any other questions? Okay, great. So yeah, let's call it a day. Have a good weekend. We can catch up on the testing a little more slowly and in more detail. I gave you an introduction today, so we'll do more detail.
Okay, thank you, Panis. Have a good
Okay,
weekend.
Praneeth, thank you. Bye.
Bye bye.
Thanks.